Every atom in your body came from a star that exploded, and the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. Lawrence Krauss. Hello, dear friends. In today's video, we would like to tell you about stars, their classification, characteristics, and life stages. Before we begin, we would like to ask you to subscribe to our channel and click on the bell icon so you don't miss new interesting videos about space and the universe. Now get comfortable and let's get started. Ancient sages loved to observe the movement of celestial objects in the night sky. Initially, astronomical knowledge was used for mystical fortune-telling, as well as for practical purposes such as refining calendars and navigation. But for millennia, knowledge remained extremely limited. People knew about stars, but not much else. Now, everything has changed. The first known characteristic of stars was their brightness. Stargazers would visually sort celestial bodies by their magnitudes. Understanding that visible brightness depended on distance, ancient Greeks attempted to determine the distance to stars based on how an object's background changed depending on the observer's position relative to the sun. However, this was only successfully done in 1837 by the Danish astronomer Friedrich Struve. After that, a correction for distance was incorporated into the estimation of stellar brightness. The next breakthrough came in the early 20th century, when spectral analysis allowed the transformation of a star's color into an exact numerical characteristic. In 1910, the famous Hertzsprung-Russell diagram was created by the Dane Ejnar Hertzsprung and the American Henry Russell. By summarizing the accumulated data, scientists discovered that 80% of stars lined up along a diagonal line stretching from the lower right to the upper left corner. This discovery had two consequences. Firstly, the diagram allowed for a rough estimation of the distance to stars based only on their apparent brightness and spectrum. Secondly, besides the main sequence, the diagram clearly showed branches. Some stars did not conform to the general rule of increasing brightness with temperature. Since then, astronomy and astrophysics have been eagerly seeking explanations for the patterns seen on the diagram. And now, it can be said that the main sequence is composed of regular stars that synthesize helium and have typical gaseous envelope. The branches on the diagram are formed by celestial objects that either use different sources of energy or differ from main sequence stars in their composition. Usually, these are either young stars still in the process of formation or old stars nearing the end of their lives. All stars form in roughly the same way. Let's take a look at how our Sun came into being. About 2% of the mass of our galaxy consists of gas and dust, mostly scattered but occasionally forming relatively dense clouds known as nebulae. Typically, such clusters are unstable, but as the gas cools down, molecule movement slows and the instability can change. The nebula begins to compress, and this process becomes irreversible. The temperature inside the cloud starts to rise, but some of the released energy is carried away by radiation, and the internal pressure cannot counteract the growing gravitational force. Our Sun first shone as a protostar, essentially a collapsing nebula. The only source of energy at that time was gravitational compression, which meant the conversion of potential energy of falling dust particles into kinetic and, consequently, thermal energy. The Sun initially shone with a cool reddish hue, but brightly, as it was roughly the size of Mars's current orbit, which provided a colossal radiating surface. Then our star entered a tumultuous stage of a young star. The Sun would alternate between collapsing under the force of gravity and expelling its outer layers into space. This continued until the hydrogen in its core transitioned into a metallic phase, and nuclear fusion reactions became continuous. Hydrogen, as it burned, transformed into helium, and about 4.5 billion years ago, our Sun reached maturity, entering the main sequence. In astronomy, stars are traditionally classified based on their emission spectrum, the only characteristic that can be directly measured. Absolute brightness and a star's mass are calculated based on this spectrum. The properties and fates of suns are determined by their membership in one of 9 weight categories. Let's take a closer look at them. Brown dwarfs are the lightest of luminous bodies. It has only recently been discovered that objects with masses ranging from 0.012 to 0.077 solar masses, or from 12 to 77 Jupiters, can be considered true stars with a nuclear energy source. The pressures in their cores are insufficient to initiate helium synthesis, but they have enough for reactions with the lowest thresholds. Deuterium and lithium serve as the nuclear fuel for brown dwarfs. However, there are significant differences between brown dwarfs and main sequence stars. The temperature and luminosity of larger stars continuously increase as hydrogen converts into denser helium and core pressure rises. Brown dwarfs, on the other hand, dim over time due to the depletion of isotopes, decreasing by approximately 15% over a billion years. When their fuel supplies are completely exhausted, a brown dwarf transforms into an enlarged Jupiter-like object. The second category includes the smallest of main sequence stars, red and partially orange dwarfs with masses up to half the mass of the Sun, sufficient for 4 hydrogen nuclei to fuse into a helium core. However, hydrogen burning in stars of this mass is still unstable. These stars pulsate. Compression leads to increased pressure and reaction intensity, but the higher energy output heats the core, causing expansion, reduced pressure, and a sharp slowdown in synthesis. Similar processes occur in the core of larger stars, but if solar activity fluctuates within fractions of a percent, the luminosity of red dwarfs can change by orders of magnitude. The least stable dwarfs are called flickering stars and are the most numerous type. Despite uneven burning as red and orange stars age, they continuously increase in temperature and luminosity until they finally change color. Lightweight stars end their careers as blue dwarfs. However, this process takes an incredibly long time, from 50 billion to 1 trillion years. Dwarfs are very frugal with hydrogen fuel, ultimately transforming into helium-rich spheres. The third category encompasses orange, yellow, and yellow-white stars of medium mass, up to 2.5 solar masses. In them, hydrogen burns steadily and luminosity and spectrum change only slightly with age. Within a range of 1 to 50 billion years, depending on the star's mass, an orange star will become yellow and a yellow one will whiten. Impressive and intricate transformations begin when the hydrogen in the core is depleted. The star's solid core begins to contract. Helium remnants squeezed out of the core briefly rekindle the reaction, causing the ejection of outer layers of matter, and the star expands to become a bright subgiant. The core, however, undergoes additional compression due to the conservation of momentum, resulting in a brief temperature spike to 100 million Kelvin. This is enough to initiate helium nuclear reaction. Helium burning in a Sun-like star ceases almost immediately, but the energy released during the helium flash raises the temperature to millions of degrees, and hydrogen burning starts throughout the star. Increasing its luminosity by 100,000 times and its radius by hundreds of times, it becomes a red giant. Afterward, the helium-enriched and heavier element-enriched hydrogen, too hot for the core's gravity to hold, escape. The helium core continues to contract, eventually becoming a tiny, super-dense white dwarf. After several billion years, devoid of an internal energy source, the white dwarf cools down and becomes a black dwarf. The fourth category includes white and blue-white stars, with masses ranging from 2.5 to 8 solar masses, which do not change their hue as they age. Significant differences from the previous type become apparent during a helium flash. Such stars do not exit the subgiant stage because stronger gravity prevents the ejection of matter, and the energy released is insufficient to ignite the increased hydrogen masses. Expansion is quickly replaced by compression, and helium burning begins in the core, turning the star into a Cepheid variable. The star pulsates with a distinct rhythm. The clear relationship between pulsation period and luminosity allows for the measurement of galactic distances using such stars. Only after helium burning in the core of a Cepheid, it contracts for the last time, igniting throughout its volume and becoming a red giant. It disperses, leaving behind a white dwarf with a mass of about 0.7 solar masses and a core of carbon, nitrogen, and oxygen enveloped in helium. Fifth category, blue-white stars with masses up to 12 solar masses also go through the stage of a yellow variable giant at the end of their life. However, they differ dramatically in terms of possible post-mortem adventures. Some believe that the remaining carbon white dwarf, with a mass of up to 1.4 solar masses, could, as it cools, transform into a giant diamond, albeit temporarily. Over trillions and trillions of years, the dwarf might evolve into an iron star, but it's uncertain whether the universe will still exist by then. For blue-white stars with masses from 12 to 18 suns, such as Antares and Betelgeuse, old age becomes a period of rejuvenation. During the yellow giant stage, they do not pulsate. Instead, they radiate steadily, burning helium in a normal mode. The stage of a red supergiant is stable for them. Even though they burn throughout their volume, hydrogen cannot escape the deep gravitational well. Not even carbon, burning peacefully in the not yet super-dense core, can disrupt the boundaries without causing an explosion. What happens when the collapsing core of a star, whose outer layers still provide additional pressure, detonates silicon, remains unknown. But it results in a supernova explosion 10 times more powerful, turning the giant's matter into a ragged nebula like the Crab Nebula, and it forms a pulsar, a neutron star with a mass of 1.5 to 2 solar masses, having a density orders of magnitude greater than that of white dwarf. Deneb, one of the brightest stars, belongs to the 7th category, blue giants with masses from 18 to 30 solar masses. Stars of this rank lose part of their mass during their formation when radiation pressure simply blows away the outer layers of the protostellar nebula, but then they still take their place on the main sequence and follow an identical path of development to the previous type, with one exception. The neutron star, formed after their extinction, with a mass of about 2.5 solar masses, is unstable, and after an indefinite period, a supernova explosion 100 times more powerful than usual may follow. The pile of neutrons compresses into a sphere 10 times smaller called a quark star. What happens in the depths of blue supergiants with masses from 30 to 80 solar masses is too terrifying to imagine. These stars erupt as supernovae just 30 million years after birth. And if 90% of their mass returns to the galactic matter cycle, the remaining 10% departs from the world. A black hole forms. Finally, blue hypergiants, luminous objects of the 9th category, never enter the main sequence. Their luminosity can exceed that of the Sun by 1,000,000 times, and their mass is approximately 500 times greater, but only at the beginning of nuclear reactions. The intensity of synthesis in hypergiants is such that radiation pressure immediately starts expelling hydrogen from the gravitational well. In their cores, hydrogen completely burns out before the star fully forms, ceasing to be young. Shedding the remnants of hydrogen into space and losing 3/4 of their initial material, hypergiants transform into a relatively stable Wolf-Rayet star, a burning sphere consisting mostly of helium. The temperature of the star's photosphere can be very high, but to an observer it appears crimson. The career of a hypergiant concludes with an impressive explosion called a hypernova, only 10 times less powerful than the collapse of a neutron star into a quark star. The nature of this explosion is unknown, but the result is the formation of a black hole with a mass up to 15 solar masses. There are still many unanswered questions about stars in the human understanding of the cosmos, but in astronomy, that's the norm. Knowledge is limited, the universe is infinite. Orbital and ground observatories tirelessly sift through countless celestial objects, uncovering new mysteries of space. Since we can only look at the stars, at least this process should never become dull. Thank you very much for watching. If you enjoyed this video, don't forget to like it and subscribe to the channel to stay updated on new exciting videos about the universe. Feel free to comment on what you would like to see in future videos. Thank you, and see you next time.